All right, so let's get into physical development in infancy. Again, this is the third of the first 5 chapters that are on your first exam. So hopefully I will be able to get these up sometime this coming week, and which would put us Thursday or Friday to be able to take the exam. I will. I don't know if, yeah, we'll probably just do it on campus probably next Tuesday. I think that would be good. Give you guys a little bit of time to go over these and be able to kind of incorporate everything. Yeah, all right. Anyway, so let's get down to it. Physical development in infancy. All right. Physical growth, the rapid advancements of infancy. Infants grow at a rapid pace over the first 2 years of their lives. This is not surprising. Infants do a whole lot of growing. A lot of things are going on, physically, mentally, psychologically, during infancy, from about the first 2 or 3 years of their lives. That is second only to prenatal development in terms of the extensive physical changes that take place. So a good chunk of not only physical but also psychological and developmental changes are really rapidly occurring during this time. By the age of 5 months, the average infant's birth weight is doubled to around 15 pounds. By the first birthday, the baby's weight is tripled to about 22 pounds. By the end of the second year, the average child weighs around 4 times as much as he or she did at birth. Again, lots of growth happening. Coffee's good. So yeah, a lot of physical things going on, a lot of mental things going on. We're going to talk about some of the physical changes that happen, divisions of the nervous system and how pathways are formed in the brain and things like that. But just know that this is a very, very rapid, very, very intense time of physical development. The weight gains of infancy are matched by increased length. So not only does the infant grow in weight, he also he gets taller. This is all very elementary, obvious stuff. By the end of the first year, the typical baby grows almost a foot and is about 30 inches tall. By their second birthdays, children average a height of 3 feet. Okay. Not all parts of an infant's body grow at the same rate. So as an infant grows, different parts of their body are going to grow at different rates. For instance, the center of the body grows faster than the fingers. And you kind of start at the top and you go down. That's why infants' heads are usually so much bigger than their bodies. You start in the center and you work your way kind of out from the center. We're going to talk about each of these principles here in just a little bit, but just know that it's not a 1-to-1 ratio on what gets grown at what point. Different things are going to grow at a much different rate. Some things are going to get larger before other things even begin to really kind of come into their own and begin to really get that physical push. So infants kind of look a little bit odd, if you will, but we've all kind of learned to accept that this is what a baby looks like, and it probably doesn't even really appear even that different. Babies' heads are huge compared to the other size of their bodies. Compared to an adult's proportions, they are very, very top heavy. So a lot of times babies will not only do they not have the muscular control to be able to walk and things like that, their head is actually a good chunk of their weight. The brain and everything that is contained in the head is very, very important, and that has to be very, very developed before the baby is born. At birth, the head accounts for 1/4 of the newborn's entire size, so their head weighs 25% of their entire body. Like I said, babies' heads are really, really abnormally, freakishly huge. During the first 2 years of life, the rest of the body begins to catch up. So the head is really what grows kind of first, and that really makes a lot of sense. when you think that, the brain is kind of in control of everything else. So it's got to kind of take its bait first. The brain's going to develop what it needs to develop in order to kind of kickstart the rest of the growing process. By the age of 2, the baby's head is only 1/5 of body length, and by adulthood, it is only 1/8. So again, it's not that the head is actually shrinking; it's that the rest of the body is catching up to the developing size of the head, which usually gets developed first. There are also gender differences in weight and length. Girls generally are slightly shorter and weigh slightly less than the boys. Differences that remain throughout adult childhood and become considerably greater during adolescence. So again, this is all in preparation for puberty, when males generally become bigger and heavier than girls. That's kind of an evolutionary pressure that was placed on men to be able to physically protect their the females and the children. That was a lot of women were, back in the caveman days, a lot of women were dependent on the men to save them from saber-toothed tiger attacks and things like that, because simply men were genetically predisposed to have more muscle mass and to be able to have a larger body size and things like that. Other animals, the opposite really kind of holds true. If you look at spiders or something like that, the females are usually much, much larger than the males. You have this little dinky little male and this ginormous, very intimidating female. So it's not that all males are bigger than females, but it just so happens that in humans that is usually the case. The 4 principles of growth. The disproportionately large size of infants' heads at birth is an example of one of the 4 major principles that govern growth. These 4 principles are the cephalocaudal principle, the proximal-distal principle, the principle of hierarchical integration, and the principle of independence of systems. So we're going to talk about what each of these here are in turn. The cephalocaudal principle states that growth follows a direction and pattern that begins with the head and upper body parts and then proceeds to the rest of the body. This is kind of what I was saying before. The first thing that's going to develop is the head, and the head's going to grow and can kind of take its goodies first, because that's where the brain is located. So again, infants' heads are usually very, very large compared to the rest of their bodies, and the cephalocaudal, the cephalo is the head, and the caudal is the body. So the growth pattern starts at the head and it continues to go down and down and down. This principle means that we develop visual abilities located in the head well before we master the ability to walk closer to the end of the body. And this again is an evolutionary pressure that's placed on us to help in our survival. The proximal-distal principle states that development proceeds from the center of the body outward. This is, again, what we were just talking about, how things that in the center are going to develop first. This is where your lungs are and your heart is and things like that, and then that's going to proceed outward. So something like, the lungs or the heart are going to develop more rapidly than, the fingertips or something like that. The proximal-distal principle means that the trunk of the body grows before the extremities or of the arms and legs. Furthermore, development of the ability to use various parts of the body also follows this principle, such as use of the arms precedes use of the hands. So as it becomes more and more out to the side, then the development becomes later and later and later. The principle of hierarchical integration states that simple skills typically develop separately and independently, but that these simple skills are integrated into more complex ones. For example, the relatively complex skill of grasping something in the hand cannot be mastered until the developing infant learns how to control the movement of the individual fingers. So this is basically a fancy way of saying you have to walk before you can run. You have to learn to develop the arm and be able to move and control the movement of the arm before you can learn to control the movement of the hand, before you're able to learn control of the fingers. And all of these things must work in concert so that you can reach out and grab something and have the hand-eye coordination to be able to do that. And finally, the principle of the independence of systems suggests that different body systems grow at different rates. For instance, the patterns of growth for body size, the nervous system, and sexual maturation are quite different. So again, nervous system development happens usually pretty early, but it continues to develop throughout childhood and even into adulthood. But it's like sexual development doesn't happen until puberty, when the child is usually 12 to 13. So that's usually one of the later things that develop. All right, the emerging nervous system. The nervous system is the body's electrochemical communication circuitry made up of billions of interconnected cells. The human nervous system is likely the most intricately organized aggregate of matter in the known universe. A single cubic centimeter, about the size of a sugar cube, of the human brain consists of well over 50 million nerve cells, each of which communicates with many other nerve cells in information processing networks. So much like a computer network where one computer can talk to another, and kind of like the World Wide Web where everything kind of grows exponentially, each of these nerves connects to several others. And each of those others also connects to several others. So from one nerve, you can kind of get a branching, exponentially growing network of nerve connections. And there are a mind-boggling amount of these nerves and these nerve connections within the brain. And so one nerve can communicate with millions or perhaps even billions of others because of these interconnected webs. And you can get information from one part of the brain to another part of the brain, from one part of the brain to another part of the body very, very quickly and very, very accurately. Another sip of coffee. That's good stuff. All right. Several extraordinary characteristics allow the nervous system to direct our behavior. These are complexity, integration, adaptability, and electrochemical transmission. The first is complexity. The brain and nervous system are enormously complex. The brain itself is comprised of billions of nerve cells. And the orchestration of all of these cells is an awe-inspiring task. How all of these things are put together, and how each nerve cell communicates with others, and how it knows which pathways to take to recall a memory, or which pathways to take to produce a smell or to move an arm, is literally, if you could see it in action, you would be humbled. It is just awesome how complex and how integrated all of these things are, and how it's like the most powerful supercomputer on steroids. And one of these things can communicate with several others, and they're all connected. And how one thing can influence hundreds of millions or even billions of other nerves, not only in the brain but also throughout the entire body. Integration. The brain does a wonderful job of pulling information together from sounds, sights, touch, taste, smells, hearing, genes, environment. The brain integrates all of these as we function in our world. So as you take in information from the outside world, all of that has to be processed, and all of that has to be kind of categorized, and decisions need to be made, and actions need to be initiated. All of this happens in microseconds. If you put your hand on a hot stove, that communication has to travel from your fingertips all the way up to through your arm, into your chest, up your neck, into your brain. That has to be processed, that, hey, this is hot, this is dangerous, I need to move. And then that movement signal has to travel all the way back down from your brain into your neck, into your chest, down your arm, into your fingertips. The muscles have to contract and move your hand. That happens instantaneously. It is just completely... I can't even begin to describe what exactly is going on, and how this... just got an email, sorry. And how all of this works together. And if you can kind of just sit there and imagine, all of the things that go together, that we process, and that happens, and the things that we think about, and even like recalling a memory, is a communication from one brain cell in the brain to another. And all of that goes through these pathways and these nerves, and it's kind of like really like a spider's web. And the internet, one computer can go and access tens of billions of others just by the click of a mouse. And that's kind of that's a pretty good analogy of what's really going on. And it's just that the nervous system is basically just the body's communication circuitry. Allows the body, one part of the body, to communicate with another, and that's really all that it does. The brain and nervous system have different levels and many different parts. Brain activity is integrated across these levels through countless interconnections of brain cells and extensive pathways that link different parts of the brain. This is what we were just talking about. Each nerve cell communicates on average with 10,000 others, making up literally miles and miles of connections. That's average, 10,000. Some do less, some do more. Usually the more important or the more pressing a certain connection is, the fewer nerves that get involved with that. Obviously, the longer it has to travel, the more time it's going to take. So things like, heart regulation and digestion and things like that, those tend to be pretty needing communications. So those tend to be relatively simplistic. My computer's making weird sounds again. So that tends to be something that is relatively simple for the nervous system to be able to communicate. Whereas things like thinking or processing memories or things that don't really have to do with our survival, those tend to be a little bit more complex and they tend to be a little farther down the line. The third is adaptability. Our brain and nervous system together serve as our agent in adapting to the world. Although nerve cells reside in certain brain regions, they are not fixed and immutable structures. They are constantly adapting to changes in the body and the environment. This is called plasticity. This is what happens when you lose your sight and your hearing is increased. Other parts of the body can kind of rise up and take up the slack. If you have a stroke and part of your brain is damaged, other nerve cells can kind of reroute those connections and work around it. And some of the functioning can actually be reestablished through things like therapy and practice. You might have to learn how to walk and talk and do things like that again. You have to kind of reestablish it and kind of forge new pathways in the brain and form new connections and kind of learn to strengthen and depend on those connections. But it is possible. Other parts of the brain can remove and readapt, and they can kind of route information around that damaged part. So it's really quite extraordinary how things like that are able to not really heal themselves. Once a nerve cell is gone, once a brain cell is gone, it's gone forever. You'll never grow that back. But other things, the brain is such an adaptable, is such a plastic organ that it doesn't, you'll never really get full capabilities back. But you can recover. You can learn how to walk again, learn how to talk again, things like that are able to again kind of reroute and forge these new pathways to get something done. If a signal required transporting from one brain cell to another, then it can kind of reroute that and be able to overcome that deficit. Much like if there's a wreck on the freeway, then you can kind of find another way to get to your destination. It might not be as fast, it might not be as efficient, but there may be stoplights or stop signs, but you can eventually get there. Just because the main pathway has been damaged doesn't mean that everything is lost. And finally, we have electrochemical transmission. The brain and nervous system function essentially as an information processing system, powered by electrical impulses and chemical messengers. Epileptic seizures are the result of abnormal electrical charges in the brain, much like electrical surges during thunderstorms. So, how nerve cells communicate with each other. It starts out as kind of an electrical signal that travels down the nerve. We're going to talk about how that happens here in just a little bit. And then once it reaches the terminus of the axon, it has to be converted from an electrical signal into a chemical signal, which bridges something called the synapse. We'll talk about that also. And then once it reaches the dendrite of the next neuron, it has to be reconverted from a chemical signal back into an electrical signal, and then it travels the length of the next neuron until it reaches the terminus, in which case it's converted again and again and again. And this happens instantaneously. All right, pathways in the nervous system. As we interact with and adapt to the world, the brain and nervous system receive and transmit sensory input. They integrate the information received from the environment, and they direct the body's motor activities. Information flows into the brain through sensory input, It then becomes integrated within the brain and then moves out of the brain to be connected with motor output. So this is, again, kind of like what we were talking about when you put your hand on the on the stove. Then those different signals have to travel up your arm and into your chest and into your neck and follow those nerve pathways from your hand to your brain, and then from your brain back down to your hand. The nervous system possesses specialized pathways that are adapted for different functions. Two main types of nerves. The first are afferent nerves, or sensory nerves, and these carry information to the brain. So it goes from the body to the brain. So back to the hand on the burner example. Once you place your hand on the burner, the sensory nerves in your fingertips quickly assess that this is hot and that something should probably be done. So these sensory nerves carry that information from your fingertips up your arm, into your chest, up your neck, and into your brain, where the brain then processes this information and decides that, hey, this is hot, this is not good, I'm going to send a signal down the pathway again to the muscles in the arm for movement away from the source. And so you have the sensory afferent nerves that carry information from the body, the hand, up into the brain. And then you have your efferent nerves, or your motor nerves, that carry the movement command back down from the brain to the body. This is done through things that are called neural networks, and we've kind of talked about these networks of how one nerve cell is connected to another, is connected to another, is connected to another, and it kind of passes the baton up the chain. Divisions of the nervous system. There are two primary divisions of the human nervous system. The first is the central nervous system. This again should all be reviewed for you if you've taken any kind of even junior high biology. You've probably come across these at one point. Central nervous system, brain and spinal cord. Boom, that's it. These encompass more than 99% of all nerve cells in the entire body. Most of them obviously are located within the brain. And then if it's not the brain and the spinal cord, it is the peripheral nervous system. So all of the nerves, running down your, that control your heartbeat, and all of the nerves that run down your arms and your legs, and that control your eyes, and that control your tongue, and that control your neck and your legs and help you walk, all of those. That's all peripheral nervous system. So if it's not brain and spinal cord, it is peripheral. End of story. Now we take the peripheral nervous system and we divide that again into the somatic and the autonomic. The somatic nervous system consists of sensory nerves, whose function is to convey information from the skin and muscles to the CNS, the central nervous system, and the motor nerves, whose function is to tell muscles what to do. So these are the really kind of the body nerves, if you want to call them that. Those things that you have voluntary control over. You can move your arm, you can blink your eyes, you can wag your tongue, you can walk forward, you can walk backwards, you can sit down, you can stand up. All of those things, those are all somatic nerves. The autonomic nervous system is the division of the peripheral nervous system that communicates with the body's internal organs and monitors processes such as breathing, heart rate, and digestion. These are things that are automatic. That's how I remember it. Autonomic is automatic. It's the thing that controls your heartbeat, that lets you digest your food. You don't have to consciously go in and control your stomach muscles to be able to process and digest your food and pass it down into your small intestine and your large. That all happens automatically. Some things you can kind of take over, like your breathing. You can sit there and you can hold your breath, but most of the time it's processed automatically. It's got the autonomic nerves kind of take care of that. And so, you're going to breathe while you're sleeping, etc. So you don't have to consciously breathe in, breathe out every single time. That just happens automatically. The blinking of your eyes, that's another one that you can kind of switch off from autonomic to somatic. You can close your eyes or you can hold them open, but for all intents and purposes, for the most part, it's done something that's just done kind of automatically. You don't have to really think about it. The autonomic nervous system. Okay, so we've got the peripheral nervous system, that's broken down into the somatic and the autonomic, and then we've got the autonomic nervous system that's broken down into the sympathetic and the parasympathetic. The sympathetic nervous system is the division of the autonomic nervous system that arouses the body, the fight or flight. This is the part of you that gets you excited. that part of your body that when you start to run or you start to exercise, you start breathing more heavily, you start to sweat more. These are all things to kind of get more oxygen to your muscles, and your heart beats faster. That's all automatically processed. You can't really control that. It's something that's all governed completely by the autonomic nervous system. And then the parasympathetic nervous system is the division of the autonomic nervous system that calms you down. So your sympathetic nervous system is that excitatory, that part of your autonomic nervous system that gets things going, and then the parasympathetic kind of calms that down and restores. Once you stop running and you sit there and you rest for a little bit, your breathing returns to normal, your heart rate returns to normal, those types of things. That would be well within the realm of the parasympathetic nervous system. That's what actually kind of comes in to slow that down. All right, neurons. Within each division of the nervous system, nerve cells, chemicals, and electrical impulses work together to transmit information at speeds of up to 330 miles per hour. Wow. So when I say that these things happen very, very quickly, that it's not a joke. Usually, again, the more life-threatening things, the moving the hand away from the burner and things like that, those are going to travel much, much faster than things that are not. There are two types of cells in the nervous system, neurons and glial cells. Neurons are nerve cells that are specialized for processing information. They're the basic units of the nervous system. So the nerve cells are the ones that really kind of do all the work. They're the ones that carry all of the messages from one neuron to the next. They're the ones that are really responsible for preserving the integrity of the message and passing it on to the next neuron. So it's kind of like a runner in a relay race carrying that baton. It's his responsibility or her responsibility to hold on to the baton and not drop it, and then to make sure that they pass it on to the next one without incident. Oh, and then the second type are glial cells. Glial cells are cells that provide support and nutritional benefits to the nervous system. So these are kind of like the support staff, if you will, making sure that the nerve cells are nourished and that they are working properly. They're responsible for repairing nerve cells if they need that. Just kind of keeping nerve cells happy and able to do their job much more efficiently. Most neurons are created very early in life, but their shape, size, and connections can change throughout the lifespan. So again, this is kind of what we were talking about before, how every single memory and every single process that you make is the result of a connection between one nerve cell and many, many others. And how those, every time you learn something new, every time you remember or memorize something, or you hear a song you like or anything like that, that is the actual result of a new physical connection between sets of nerve cells, connections that were not there before. And things like education and the ability to think and the ability to process more information, the ability to look critically at things, those are all very, very sophisticated. They're kind of the result of very, very sophisticated ways that your nerve cells in your brain are able to communicate with each other. And the more connections that get from one point to the other, the more easily that memory is recalled. So you really don't ever lose a memory, if you will. It's still there, but sometimes the connections become weakened and weakened and weakened if they're not used a lot. So if you have trouble remembering what you ate for dinner, and on July 3rd of 2012, that's not something that you really put a lot of effort into building a whole lot of repetitive connections on. As apart from, say, like something like your social security number, which most of us can recall at will. That's something that you need to be able to recreate. You need to be able to remember, and so that might have 15 or 20 different connections, different pathways that get from to the kind of the end result, the location of the treasure, if you will. If you kind of think about it, in that treasure map metaphor, how the memory or the recall or something like that is actually the location of the treasure. There may be 50 or 75 or 2,000 different ways that you can get from where you are to that location to be able to dig up the treasure and recall the memory. But if it's not something that you do often or something like that, then you may lose the ability to kind of travel down those nerve pathways, especially if it's something that you didn't put a lot of effort into building those connections. And sometimes it takes quite a bit of effort. This is why studying and things like that, practice. If you want to learn to play a musical instrument or whatever, you have to continue to practice and practice and practice and build those connections and strengthen those connections and reinforce those connections, because it's something that is the more you do it, the more the stronger those connections become and the easier they are to recall. Every nerve cell or neuron has three parts: a cell body, a dendrite, and an axon. The cell body contains the nucleus, which directs the manufacture of substances that the neuron needs for growth and maintenance. This again kind of helps the nerve cell regulate itself and helps make sure that it's able to carry that information from the dendrite through the cell body, and it kind of makes the decision to whether or not to send that information down its axon to the next nerve cell. We'll talk about that a lot more here in just a second. So the cell body is kind of the central nucleus of the cell, if you will. Dendrites receive information and orient it towards the cell body. So the location, the direction of travel across a nerve cell from one end to the other is always the same. The dendrites are kind of these, there are many of them, and they'll kind of spider out like that. And it looks like kind of like the mouth of a river. If you've ever seen a picture of like the Nile River in Egypt, how the mouth of the Nile River, it kind of has a delta, and it will kind of spider off, and there'll be several outputs, and that's exactly what a dendrite looks like. You can look it up and see what they look like, but that enables multiple avenues for induction of the nerve of the signal, in order to be kind of brought in and pushed into the cell body. And then the cell body kind of analyzes that signal and decides whether or not it's important enough to send to the next nerve cell. And it does that by, again, processing the information that it receives from its own dendrites, because again, that information is always oriented inward. And then if it decides that it's something that needs to be passed on to the next nerve cell, then it will fire it out on its own axon. An axon is kind of a long, they're usually singular, but it's usually a kind of a tight grouping of nerve fibers, and that is what kind of carries the signal from the cell body out and enables it to pass on to the next nerve cell. I kind of see it like almost like a fighter jet taking off from an aircraft carrier or something like that. How it's a very fast, very sudden thrust of information, and that's kind of how I see the axon in kind of my mind's eye, and how I'm able to kind of picture how this is kind of all working together, and how it really makes things go and makes things happen. So those are the three parts of the nerve cell. Again, you might want to kind of look up a picture of a nerve cell if you're at all curious, and once you see exactly what it looks like, you'll understand exactly what I'm talking about. It's kind of hard to describe. So if you're curious at all, just search axon in Google, and there'll be a billion pictures of it. A myelin sheath, which is a layer of fat cells, encases and insulates most axons, not dendrites, axons. By insulating axons, myelin sheaths speed up transmission of nerve impulses. Axons without myelin sheaths are not very good conductors of electricity. With the insulation of myelin sheaths, axons transmit electrical impulses and convey information much more rapidly. So again, we're talking about electricity here. So if you think about, the casing, that plastic casing on the outside of speaker wires, that helps kind of insulate the actual wire itself, so that dissipation, because electricity wants to get out. It doesn't want to flow across. It wants to get out as fast as possible. And so if you take off that plastic, then that really defeats the purpose of the speaker wire, or of the wire or the nerve at all. A lot of the signal will be dissipated out, and it won't be nearly as strong, and it will lose some of its kick. It will lose some of its importance. And so axons are, it's kind of this layer of fat, and the best way to think about it is kind of that speaker wire, or the wire on the telephone pole, the telephone electrical wires. Those are also insulated because it helps diminish the ability for the electricity to kind of escape out, and it keeps that very that fighter jet, lightning fast, very efficient, very single-mindedness of this transmission. It kind of really makes it a lot more efficient and a lot better at passing its signal on from one neuron to the next. Multiple sclerosis. If you or anyone you know has multiple sclerosis is a degeneration of the myelin sheaths of the nerve cells. And so people with multiple sclerosis, their nerves do not work as well. And so they'll oftentimes have cognitive issues, or in extreme cases they'll lose the ability to walk, or to eat, or to swallow, or anything like that, because their nerves are not able to really communicate very well with each other. And so a lot of the transmission gets bled out, and the nerves aren't really able to communicate with each other nearly as well. And a lot of problems can really come from that. So those myelin sheaths are very important in enabling nerve cells to very efficiently and very powerfully communicate with one another without a whole lot of that bleed off, that loss of intensity and signal that occurs when the myelin sheath is not there. Axons fire on an all or none principle. Once the electrical impulse reaches a certain level of intensity, called the threshold, it fires and moves all the way down the axon without losing any of its intensity. Again, that's if the axon is properly myelinated. So again, once the cell body kind of makes the decision to communicate, to send that on, that it's a signal that needs to be sent on to the next, then it will send a signal down the axon, and much like the fighter jet going all the way across, taking off on the aircraft carrier to do its thing. That once it starts, it goes. There's no turning back. The cell body can choose to terminate a signal, but once it makes the decision to send it, and it starts to send it, it goes. There's no stopping it or turning it back or slowing it down. And that level where the nerve cell makes the decision, if the intensity of the message is strong enough and it reaches beyond a certain level of importance or a certain level of intensity, then the cell body kind of flips that switch and makes the decision to send that on, and again it shoots it down the axon, and there it goes. So what happens when a neural impulse reaches the end of an axon? Neurons do not actually touch each other directly, yet they still manage to communicate. So the axon of the sending nerve does not actually touch the dendrites of the receiving nerve. There's a small little gap in between those. That gap is called a synapse. Synapses are tiny junctions between neurons. The gap between neurons is referred to as the synaptic gap. So there's no physical contact between the axon of the sending nerve and the dendrite of the receiving nerve. Before an impulse can cross the synaptic gap, it must be converted to a chemical signal and carried by something called a neurotransmitter. So this is kind of where the electrochemical transmission, we were talking about earlier about how the nerve signal starts as an electrical impulse, and then once it reaches that synaptic gap, it's got to be converted into a chemical signal, carried, kind of ferried across the river, if you will, by the neurotransmitter, which docks it into the dendrite of the receiving nerve, and then that chemical signal is decoded by the dendrite and reconverted to a chemical signal when the dendrites then pull it into the cell body, where if it reaches its threshold, the cell body continues to send it on down the axon, and so on and so forth. These neurotransmitters transmit, quote unquote, the signal being relayed from one neuron to the next across the synaptic gap. So these neurotransmitters, and you've probably heard dopamine, serotonin, those types of things, the happy chemicals. Those are all neurotransmitters that help cells in the brain communicate with each other. And if the brain kind of has a regulatory mechanism that scoops up extra neurotransmitters in the synaptic gap that it doesn't think it needs. And so if there's not a whole lot of connections going through there, then the brain will kind of upregulate and take in more neurotransmitters because it thinks that they're not needed. And so things like, Paxil and Prozac and things like that stop the brain from doing that. They actually inhibit the upregulation. They're selective serotonin reuptake inhibitors, SSRIs. So they stop the brain from kind of correcting what it thinks is a mistake. And it leaves those neurotransmitters there so that they're able to continue to carry those signals along the pathway, and you feel better. Nutrition in infancy. We talked a little bit about nutrition in the last maybe the first chapter. Nutrition, especially like prenatal nutrition, the mother's nutrition, and things like that. What the mother eats, the baby eats. But nutrition in infancy is also very, very important to the child itself. You're starting to, again, there's a lot of physical changes that are happening. So children need their vitamins and minerals and their Wheaties in the morning, because if you're not properly fueled, then you're not able to do the physical work that is needed to create a new body. So nutrition, getting that proper the proper vitamins and things like that's very, very important. The rapid physical growth that occurs during infancy is fueled by the nutrients that infants receive. Without proper nutrition, infants cannot reach their physical potential, and they may suffer cognitive and social consequences as well. Not to mention, you're creating eating habits that they will likely carry with them for the rest of their lives. So if you're feeding your child junk food and things like that, don't be surprised when they grow up and they tend to favor those foods. On the contrary, if you're feeding your child vegetables and healthy foods like that, then that is also what they will learn to like and how they will continue to eat when they become adults. Although there are individual differences in what constitutes appropriate nutrition, some broad guidelines do hold. In general, infants should consume about 50 calories per day for each pound that they weigh. That's, again, kind of an average. An allotment that is twice the suggested caloric intake for adults. And this is really because a lot of things are happening. A lot of activity is going on, a lot of physical development, and the body is using a whole lot of calories building a body. Excuse me. While there is no clear association between obesity during infancy and obesity during adolescence, some research suggests that overfeeding during infancy may lead to the creation of an excess of fat cells, which remain in the body throughout the life and may predispose a person to be overweight. So again, once the body creates a fat cell, it's there for good. You can kind of decrease the volume of that fat cell and kind of deflate it, and that's how a person loses weight. But once the body creates a fat cell, it is there, ready to be filled again. That's why it's hard to keep weight off once you lose it. Weight during infancy is associated with weight at age 6 and adult obesity, suggesting that obesity in babies ultimately may be found to be associated with adult weight problems. This kind of, it goes back to something called a set point, where, your body kind of regulates where it thinks your weight needs to be. And if you continue to eat more and more calories than you burn, then your body's going to slow down your metabolism, because you're not really needing all of those calories because you're not very active. And once your metabolism slows down, then you don't need nearly as many calories to maintain the same amount of weight. But if you continue to eat the same that you did, combined with the slower metabolism, then you can see that really is a recipe for obesity and health problems later on. If you take in more calories than you expend, the excess calories are going to be stored as fat. Simple as that. However, although the data do not clearly link overweight babies with overweight adults, parents should concentrate less on their baby's weight and more on providing appropriate nutrition. So don't, babies eat a lot. They can. They're supposed to. So don't really focus on, if your baby's a little chubby or something. Don't start to kind of restrict their food in order to keep them at a healthy weight. They will eat what they need, and their body will use what is needed. Because again, there's a lot more going on in an infant's body than there is in an adult's. For the first 12 or so months of life, there is no better food for an infant than breast milk. Breast milk is king. It is the gold standard. It is the absolute best thing that you can feed your child. It has all kinds of antibodies and all kinds of nutrients and things that are passed from mama to baby that you really can't get with formula or anything else. Baby food. It's just not the same. Breast milk is the best. Breast milk not only contains all the nutrients necessary for growth, but it also seems to offer some immunity to a variety of childhood diseases. So things like mother's antibodies, all of the disease prevention things that she has gotten, that is able to be passed on to the child. That there is a reason that human females are able to produce milk, and that milk is available for the child. That is a biological evolutionary thing. And it's there for a reason, so it needs to be used because again, breast milk is the best. There's just no ifs, ands, or buts about it. Breastfeeding also offers significant emotional advantages for both mother and child. So breastfeeding is an opportunity to bond. It releases chemicals like oxytocin, which is kind of the bonding, the loving, the nurturing chemical that makes you want to cuddle and makes you want to bond. That's a very important intimate time between mother and baby. Mothers have a connection with their children that fathers never will. Not only do they carry them in their body for 9 months and feed them and kind of build that there's a physical connection there, but there's also this ability that mothers have to kind of connect with their child on a level that is different for dads. We just don't possess that link, that key. Dads, of course, love their children, but it's nothing. The connection, the intimacy between mother and child is vastly different and really, I would guess, more important than the intimate connection between father and child. Okay, that is chapter 3. So again, I will work on getting chapter 4 updated. These notes it's a big, long production, so it's not something that can be done on the fly. So forgive me for not getting these out much sooner, but it's an all-day affair. So let me work on chapter 4 and chapter 5. Make sure that you check the Canvas, the website, for the videos that are also kind of on the same page where you get your notes. Make sure that you watch all of the videos for the first exam, because it's looking like your first exam will be a week from this Tuesday, and we will meet on campus for that exam, 11 o'clock. So that exam will be in person. That will be one of the 3 things that we need to do to meet in person. I'm not sure if they've lifted the restrictions for class size. When the semester started, we were only able to have classes at, I think, 50% capacity, which is why this whole thing is being done online. But they want us to meet on campus, I think, at least 3 times. So that will be one of them. And then once you have your first exam, there are 4 chapters for your second exam. Hopefully we'll be able to get through all 4 of them. This was a shortened class. I'm not sure exactly how they expect us to get through all this information in 6 weeks, but so I will do my best, and it may be kind of a marathon sprint to get that second exam done, and then we'll race right to the final, and that will be that. Again, I will take care of you guys, especially if we're not able to cover everything that we need for the second exam. The final will be cumulative, so make sure when you get this exam, make sure that you hang on to it, because there will be questions from the first and the second exam that will comprise the final, and they will literally be copied and pasted. So if you hang on to your exams, then you'll know exactly what questions will be on the final, and so that should be the easiest exam of your life. Again, if you have any questions, shoot me an email. Sean.Colwell at navarrocollege.edu, or just send me a message through Canvas. That's probably easier. And I will do my best to set you on the right path and answer any questions you might have. All right, so make sure that you watch these lecture videos. They take a lot to put together. So again, make sure you watch not only these videos but also the content videos on the Canvas page as well. All right, okay, I will see you guys next time. All right.